Swayam Prabha. Digital India. Educated India.
Hello all. So welcome to Astrochemistry. This is lecture 24 and this is also tutorial 6. We'll continue from where we left in the last tutorial. And in tutorial 5, we were discussing about the concept of polarity and how it is connected with the notion of obtaining spectral lines. I ended up the last tutorial by telling you that for us to get a purely rotational spectrum, the molecule should actually possess some amount of polarity. In other words, any non-polar molecule will not give rise to a rotational spectrum. Okay. On that note, let us look at a few more examples. So I'll give you a few molecules. Say for example, take the example of this is the first question for today. Take for example molecules such as benzene. Okay, right? And benzene and this is benzene where one hydrogen is substituted with a deuterium. Okay, this is C6H5D, which is an isotope of hydrogen. Okay, take CCl4 and then take the example of CHCl3. Now, among these compounds, which ones would give a pure rotation spectrum? And what is the answer? Well, first we have to look into the structure of the molecule to determine whether it's polar or not. And if it's polar, it can give a purely rotational spectrum. If not, it cannot do it, right? So let's start with benzene. What is the structure of benzene? It's a symmetric, cyclohexane. Sorry, it's a symmetric 6-membered ring system. It is planar, okay, right? So the net dipole moments cancel out due to all the CH and CCs also, correct? So therefore, would you expect any purely rotational spectrum for this? The answer is no, right? Now let's say that you substitute a hydrogen with a deuterium. In that case, there will be a small net dipole moment, right? There will be a very small amount of net dipole moment because this thing alone doesn't cancel out, right? So the answer is yes, you can for this molecule. Okay, right? And CCl4, what is the answer? Just like we didn't get it for CH4, right? CCl4 is the same as CH4. Recall in the last tutorial, we saw that for methane is a non-polar molecule. And if methane is non-polar, CCl4 is also non-polar because the structure is going to be the same with just the hydrogens substituted with chlorines, right? So the answer is, for this is no, yes, no. And what about this molecule? CHCl3. There will be a net dipole moment, right? Well, no matter what the orientation of the three chlorines are, they don't get cancelled out with the one CH. So the answer is yes. I will leave it to you as homework to actually write down the structure of CHCl3 and then look at the magnitudes of the dipole moments and see if they cancel out or not. All right. So before we actually proceed to the next question, recall that in the last tutorial, I had told you that I'll give the exact value of dBi in this tutorial. Okay. So just note 1 dBi. I had given some approximate magnitude of 10 to the power minus 30. Okay. It turns out to be correct. It's going to be something like 3.3 into 10 to the power minus 30 coulomb meters. Okay, this is the magnitude of 1 dBi, which is much less than the conventional SI units. All right, please don't see this number is to be kind of expected, right? Because this is obtained by multiplying the charge of an electron, which is 1.6 times 10 to the power minus 19 coulombs, right? Yeah, that into your if you consider, for example, the Bohr radius, okay, or something like that, okay, which is of the magnitude of 10 to the power minus 10 meters, right? So 10 to the power minus 19 and times like 10 to the power minus approximately 10 to the power minus 19 times 10 to the power minus 11 will give you this magnitude, and then you get this p factor also. So this is justified, about the magnitude that we're talking about. All right, this was just a note. Don't be confused with the question. This was just a pending quantity that I had to give from my end from the previous tutorial. All right, yeah. So we'll continue with our next question. Our next question is that I'm going to state this as a fact to you, okay, given that to obtain the vibrational spectrum of any molecule, what you need to do is we need to detect a change in dipole moment all right, please note a very important point here. Okay, we need to detect a change in net dipole moment in the molecule as it interacts with light. So please note this point very clearly. Okay, now this is a given fact. Okay, I've not told you where I got this from. This is based on selection rules obtained from quantum mechanics. Just like I gave you that for a molecule to exhibit pure rotational spectrum, it needs to be overall polar, right? Likewise, for a molecule to actually be exhibiting some vibrational spectrum, okay, right, we should be able to detect a change in its dipole moment. This is a given fact. Okay, I'm giving it, it's a fact, of course it's true, okay, right? You can verify from various sources, it's true, and its basis I'm not giving, and how exactly we derived it I'm not telling you right now. When we actually study the concepts of vibrational spectroscopy in some more detail, I will address this point in a little bit more detail, although the exact derivation itself I will not give you because that will be a full-fledged quantum chemistry course. Okay, right, okay. So this is given to you, okay. Now given this fact, the question is going to be that which of the molecules can exhibit a vibrational spectrum. The molecules given to you are N2, CH4, okay, right? N2, CH4, C6H6, CO2. Yeah, so the examples are clear enough, right? N2, CO2, CH4 and C6H6. Now, what is going to be your answer? Now, I've given to you that, to obtain the vibrational spectrum, you only need to detect a change in the dipole moment, okay, right? To begin with, the molecule can actually have a zero dipole moment. That is the key point, okay, right? The key understanding from this question, okay, given this fact and the question that I want you to take home with you is that in the case of vibrational spectrum, right, to get a vibrational spectrum of a molecule, the net dipole moment can actually be zero. For example, if you consider carbon dioxide, right? If you consider carbon dioxide, you notice that how many vibrational degrees of freedom does it have? Recall from our previous classes that the total numbers of degrees of freedom is going to be 3n, which is d total is 9, d translational is going to be how much? D translational is going to be 3, D rotation is going to be 2, and so your D vibration is going to be 4, right? Right, so from the total of 9 degrees of freedom, 3 is for translation, 2 is for rotation because it's a linear molecule, right? And the vibrational degrees of freedom is going to be 4 therefore, right? Now, from out of these 4 possible movements of vibrations, okay, right? The 4 possible modes of vibration that this molecule can undergo, correct? Those those vibrations which lead to an overall asymmetry, right? Those vibrations which overall asymmetry. By asymmetry, I mean an asymmetry in terms of the structure, okay, right? Will lead to a net dipole moment, right? Will lead to a net dipole moment. Therefore, okay, right? Therefore, what happens is that even though to begin with there is no net dipole moment, in the course of the molecule interacting with light, some vibrations, okay, right? Some vibrations are going to be asymmetric. I'm not going to get into the details yet, okay? Because some modes are going to be asymmetric, those vibrations are going to result in the generation of a net dipole moment. So you can detect a change in dipole moment, which is due to a change in the symmetry of the structure as the molecule interacts with light. And so therefore, you can have a vibrational spectrum of carbon dioxide. Note this beautiful point, okay? The key point I want to once again emphasize is that to obtain a vibrational spectrum of a molecule, to begin with, the net dipole moment can be 0. But in the course of interaction of the molecule with light, right, some particular vibrational modes can result in asymmetry, and they will overall give rise to the vibrational spectrum. Okay, please note this point. Okay, now let's consider the next example of N2 molecule to highlight. We've taken CO2 as an example, right? So for CO2, the answer is yes. To take the next example of N2, I'm going to retain this statement because it's important, okay? And I also want you to just go through this and take this in your heart, okay? This, and then the for the rotational spectrum, that the molecule should not be non-polar, the molecule should always be polar, right? These are very important concepts which shall recur in astrochemistry from time to time, okay? All right, so we're going to take the example of N2. Now, how many vibrational degrees of freedom does N2 have? Now, D total is going to be 2 3s are 6, D translational is 3, D rotational is 2, and D vibration is 1. Now, what is this 1 degree vibration? Notice that in CO2, I mean, the modes of the degrees of freedom which correspond to the various independent ways in which vibration can happen are 4. For example, you can talk about, the symmetric way in which both the O's are going together. It can happen out of plane and in plane also, and various combinations of those, okay, right? Some of them are going to result in asymmetry. But here, in N2, the number of vibrational degrees of freedom is only 1, okay? And you can imagine what it is going to be. Like I even said in the lecture corresponding to this subject, this is going to be symmetric, right? Because this is going to be symmetric, overall, no matter how much the stretching happens, okay, how much the stretching and de-stretching or like coming back, stretching and coming back happens, right? The change in the molecular geometry is always going to be symmetric, right? And due to that, in any case, we won't be able to detect any change in dipole moment. Are we clear, right? We'll never be able to detect any change in dipole moment, okay, right? So therefore, the point is no vibrational spectrum. So why did I take the specific examples of carbon dioxide and nitrogen? Well, carbon dioxide is also a molecule which contains no dipole moment, pretty much like nitrogen, okay? But despite like not having a dipole moment to begin with, all right, due to a change in dipole moment, carbon dioxide can exhibit a vibrational spectrum. Okay, but for N2, it doesn't have a dipole moment to begin with, and no matter like what vibration happens, which is of course only one mode. Okay, right? No matter how it happens, right? No asymmetry in the structure is going to be generated overall, and so the dipole moment will never change. As a result, it does not exhibit any vibrational spectrum. Clear, right? So the answer for this is no, this does not. What about CH4? It's easy to see, right? See, it's going to be a more complicated case of carbon dioxide. Instead, you have like 4 plus 1, 5. The total numbers of degrees of freedom are going to be 15. Okay, right? 15, and then minus 3, minus 3. 15 minus 6 is going to be 9. So this has like 9 degrees of vibrational freedom. Okay, right? If it has 9 degrees of vibrational freedom, not all of them can be symmetric. All right, so there is going to be some combination which is going to lead to some overall asymmetry, which means that there will be a net dipole moment change, and therefore it will exhibit vibrational spectroscopy. So I mean a vibrational spectrum. So the answer is yes to methane. And what about benzene? Likewise, right? It's an even more complicated case of methane, right? So the answer is yes here also. Okay, so the point is, with vibrational spectrum, getting a vibrational spectrum, it is not just about the initial dipole moment being 0, but the change in dipole moment should also be 0. That's when you will never get a vibrational spectrum. Okay, so therefore all the homonuclear diatomics, right? All homonuclear diatomics, for example, your H2, N2, O2, blah blah blah, right? All of them will neither give a pure rotational spectrum. I mean this ROT-SP. By SP I mean rotational spectrum. I'm running out of space here, so I'm simply writing it as ROT-SP, nor a vibrational spectrum. Okay, so I mean, because this is pretty down in the board, I'll read it again. Homonuclear diatomics such as H2, N2, O2, etc., will neither give a pure rotational spectrum nor will they give a vibrational spectrum for different reasons. No pure rotational spectrum because the dipole moment is 0 to begin with, right? And no vibrational spectrum because even though they vibrate, the vibrations will not induce a change in the dipole moment. All right. So therefore, in any case, right? In any case, there will be no spectrum. Are we clear with this? Okay. And having said all this, I want you folks to clearly and emphatically understand that I have not yet given you the reason for this. I have stated it as a fact. Okay, given, right? Yeah. So why this happens is I mean, will be clear to you. Not 100% because we won't be going through all the mathematical steps, but I'll tell you the qualitative picture behind this rationale. Okay. On that note, we go on to the next question now. This should be question 3. And this question is going to be that, recall in the lecture, okay, for linear molecules, we ignored, remember, we ignored one degree of freedom Okay, we ignored 1 degree of freedom and further did not say why. At least explain now in a tutorial, okay? Explain. Well, what is the answer? So what was the degree of freedom that we ignored? Take, for example, you take a molecule such as, I'll take a carbon dioxide, for example, CO2, right? What was the degree of freedom we ignored? It was, we ignored one degree of rotational freedom. I'm sorry, one rotational degree of freedom. I'll make it clear. So this is ROT, rotational, okay, ROT for short, rotational. So we ignored a rotational degree of freedom, and what we actually ignored was the rotation about the axis where, all the nuclei of the linear molecule lies, okay. We ignore axis where all nuclei lie, okay, right? And what are the other two axes along which this molecule can rotate? Well, one is going to be one which is the plane of the board, okay, right? We're talking about this axis right here, right? This is, of course, the plane, the horizontal line passing through the plane of the board, and there is one more axis which is going perpendicular to the board, okay? That's your rectangular Cartesian system, all right? I again tell you, we can adopt any coordinate system, but for the sake of convenience, we are using the Cartesian system which is easiest to visualize, okay? Okay, so we ignore where the axis where all molecules lie. That's the fact. But why did we do that? What is the answer? Well, the reason why I kept this question for tutorial is because it beautifully illustrates the connection between classical mechanics, spectroscopy, and astrochemistry eventually, okay, right? So you're all familiar with the notion of the moment of inertia, correct? So what is the moment of inertia along this direction? Your I, okay, let me call this like axis. This is going to be called as the axis along where the nuclei lie, okay. So the IAN, right, is negligibly small, right? Notwithstanding any asymmetry in the system, okay, right? IAN tends to 0 because your I is what? Sigma mu r square, okay, right? And your IAN is 0. And for these type of systems, I'll delete it here. What we shall soon see, okay, right? Your I along this axis tends to be 0. And for these systems, okay, we shall derive. We might skip some steps, okay, in a future lecture, that the energy, okay, right, the energy is proportional to h bar square by 2I, okay. There may be some constant depending on what unit you choose, etc., okay. But again, note the energy, okay, right, is inversely proportional to the moment of inertia for these systems, okay. Please note, and I have not derived this yet. This is to be derived in a future lecture. All right, clear? So don't ask me, where this equation comes yet. I have clearly not told you where it comes from so far, but I will tell you subsequently. Okay, please pay attention to that point. All right. So because your energy is inversely proportional to your moment of inertia, and because your I along this particular axis, your IAN tends to 0, the energy of rotation, okay, right, tends to be very large. Without like going into the exact magnitude, the energy required for rotation along the axis where the nuclei lie is tending to be infinity. Now, isn't it beautiful, right? We start off with a concept of classical mechanics, okay, rotational motion, and we connect it with a formula that is obtained from quantum mechanics, which is applied in spectroscopy, and all of it is useful to detect molecules in space. So look at the interdisciplinarity in the whole picture: classical mechanics, quantum mechanics, spectroscopy, astrochemistry. Okay, so this particular problem highlights to you why a seemingly simple fact, okay, that is that we ignore the motion along one particular axis, right, is actually based on profound fundamental ideas from several disciplines. Okay, please understand it. Okay, so as E tends to infinity, at almost all temperatures, barring very high temperatures, we're talking about, T greater than, one has to quantify it, okay, T greater than 10k Kelvin or something like that, okay, not 10 Kelvin itself, this is 10,000, 10 to the power 5k Kelvin, etc., right? We can conveniently ignore this axis as contributing to a degree of freedom, okay, and because it is such a high energy transition, so that at normal room temperature, and definitely in the interstellar medium where the temperatures are going to be predominantly low. Of course, even in the interstellar medium, we shall be encountering such situations, but therein the number density is so small. Okay, right? So more often than not, we won't be worrying about rotational spectroscopy in that region. Okay, right? But rotational spectroscopy at like low temperatures and at room temperatures, we can conveniently ignore this degree of freedom. That's it. Okay. So this is the overall explanation. Clear? And how did we solve it? We solved this problem by beautifully connecting an idea starting with classical mechanics, because I is mu r square, recall, and because r here is 0, right? It's the distance of the center of mass. All right. So therefore, I tends to 0, and we start off with this idea, and we use a quantum mechanical idea to get this expression, which I have not yet shared with you in this course, to tell you why this axis can be absolutely ignored. But it is not to be ignored always. It is not to be ignored at room temperatures and temperatures which are very low. All right. At very high temperatures, if like you have enough energy to supply to this molecule, right? Then of course, then even that degree of freedom will be activated. All right. Are we all good with this? On this note, we shall proceed to the next question. This question is going to be the last question for this tutorial. This question will be based on some structural features. So for example, when we discuss the molecules that are available in space, okay, we discussed molecules found in space, that is molecules detected in the ISM. We saw a molecule of the form, right? This was the first, recall, this was the first chiral molecule detected. Although, the molecule overall detected was not chiral, because an equal and opposite amount of enantiomers were detected. Okay, right? So this molecule was, what is it called? It's called as propylene oxide. I'm going to call this PO, propylene oxide. Okay, this was detected. Now, the question is, what are the ways via which this molecule can react? How all can it react? Why is this question relevant? This question is relevant because it tells you how principles of chemistry, principles of reaction mechanisms will be helpful in detecting how molecules evolve in space. Okay. Now, what are the possible ways in which this can react? Well, one is to, coordination with oxygen. If you have any electropositive species, such as a metal or something, you can coordinate with oxygen. And after that, the other mode is going to be via opening of the ring. Well, how can that happen? Say, for example, you have some nucleophilic species attaching here, right? Now, this will relieve the ring of its strain. This will relieve the ring of its strain. Why is it ring strain? This ring is strained because, recall, based on your fundamental chemistry principles, well, this carbon is going to be sp3 hybridized, okay? And an sp3 hybridized carbon has a normal bond angle, equilibrium bond angle of close to 108 degrees. What is it here? It's constrained in a ring, right? Because it's constrained in a ring, it would want to open. It would show a natural propensity for the ring to be opening, okay? So the various ways via which the chemistry can happen here is attack on the oxygen, or by various nucleophiles opening the ring itself. Okay. Now, why is this relevant? This is relevant because this molecule, because it has the possibility to be chiral, right? This can lead to the formation of more chiral molecules in space if it were chiral. Okay. So these are the various modes that need to be looked into for the future researcher if he or she is interested in understanding molecular evolution. Okay. So it is to understand the chemical principles behind molecules in space that I gave this particular example. All right. So on that note, we end this tutorial also. And in this tutorial, we looked at problems ranging from connecting classical mechanics to spectroscopy and astrochemistry to some structural features. More such features will follow in subsequent tutorials. And in the next lecture, we shall look at how molecules are detected in space. Okay. We looked at how atoms were detected in space via absorption and emission spectroscopy, right? Now that we have an understanding of the various types of motions of molecules, we shall look at how molecules are detected in space in the next lecture. Thank you so much.